Welcome to solving exponential equations where we can't rewrite the base. Right, so these are going to require a few formulas. We're going to need the change of base formula because sometimes our equation may be written in a base that's not so easy to work with. So we can change it to a base that is easy to work with in the calculator, namely base 10 or base e, the natural log. We're going to be using our inverse properties. So if we have a log in a base and the result is the exact same value, we know that that's going to be equal to 1, because that's basically saying, what would I have to raise 2 to get 2? Right? Well, that's just the first power. Right? And the same thing here, what would I have to raise e to get e? Well, that's just the first power. We'll also use the power property, that exponents can move in front of logs, because they're both exponents. A log's an exponent, and the power on the result there is also an exponent. So when we raise power to a power, we multiply exponents. So log x to the n power is the same as n times log x, because log x is an exponent and n's an exponent. All right, so here's our first problem. All right, so I'm going to maybe move the screen up, and then I'll move it down. I think you see the screen up there. Oops, now it's too high. All right, so we have e to the negative x minus 6 equals 9. All right, here's our problem. We need to isolate the exponential equation, the exponential expression, I should say. So we need to isolate e to the negative x, so we're going to add 6 to both sides. So now we have e to the negative x equals 15. And notice that you can't rewrite the number to have the same base. You can't write 15 as e to a power. E is an irrational number, and you certainly can't write e as 15 to a power. Right? So you can solve the equation by taking a logarithm of both sides. So you can't rewrite the number to have the same base, but you can solve by taking a log. All right, so our bases are going to have to match. So whatever the term is that has the exponent, right, that's the base of our log. So it's e that has the exponent. Right? So that means that we have to take the natural log of both sides. All right, so we're going to take the natural log of both sides. Now we can use the power rule. The exponent moves in front. But natural log of e, well, that's just 1. So this is just saying negative x times 1. Well, that's just the same as negative x. You're going to have to use a calculator to get natural log of 15. All right, so natural log of 15 is 2.708 to the third decimal place. And we were solving for x, so we're just going to have to divide both sides by negative 1. And then we have our answer. All right, and that's all there is to these. All right, so when we can't rewrite them, we're going to use logarithms and properties of logarithms to help us out. Here's the next one. All right, so we have 6 to the 2x equals 1500. All right, I can't write 6 to equal 1500, even if you weren't sure of the powers of 6. If you multiply 6 by 6, you're going to get a number that ends in a 6, right? Like 6 squared is 36, and 6 cubed is 216. It's never going to end in a 0. Right? So you're not going to be able to write these so they have the same base. So what you're going to do is take a log of both sides, because a log is the inverse of an exponential, and we'll be able to free our exponent. All right, so our base is going to be 6, right, because that's the term that has the exponent, with the variable and the exponent. So we're going to take log base 6 of both sides. So now we have log base 6 of 6 to the 2x equals log base 6 of 1500. The exponent can move in front using the power rule. So we have 2x times log of 6 to the 6 2x power, right? It moved in front and it decided to stay there too. All right, so 2x times log of 6 of 6 equals log 6 of 1500. All right, that was just the power rule. We know log 6 of 6, that's just 1, so we can replace that with a 1, and you don't really need to write 2x times 1. So we have 2x equals log 6 of 1500. But now the exponential equation is not the common log, not base 10. It's not the natural log, base e. So now we're going to have to use our change of base formula to write this into a form that we can work with. as I'm moving these up so you can actually see it. So we have 2x equals, change of base formula, it's going to be the log or natural log of the result over the natural log of the old base. So we have log 1500 divided by log 6. And you just use a calculator. So you have 2x equals 4.0816. And somewhere hidden way down here is our final answer. We just divide by 2. And so now we have x equals 2.04008. I think everything moved. I think that was it. Oops, there we go. Divide each side by 2. I thought there might be a divide each side by 2 somewhere. There we go. All right, so now we have solved this problem. So these are going to require a calculator and some of the properties of logarithms to solve. Right. Let's look at another one. All right, so here we have 3 to the x plus 4 power minus 2 equals 99. We have to add 2 to each side so that we can isolate the exponential expression. So now we have 3x plus 4 equals 101. Well, 101 is a prime number, so you're never going to be able to write 3 as, 101 as 3 to a power. So we're going to have to take a log of both sides. And of course, the base is going to be 3, because 3 is what has the exponent with the variable on it. So now if we take a log, base 3 of both sides, we have log 3 of 3x plus 4 equals log 3 of 100. Now the exponent can move in front, right, using the power rule. So now I have x plus 4 times log 3 of 3. But log 3 of 3, that's just 1, so I don't need that. So now I've got x plus 4 equals log 3 of 101. And, well, log 3, that's just, base 3 is really just not a very friendly base to be working in. So we want to change it to either natural log or to log base 10. It doesn't make any difference which one you choose. All right, so we have x plus 4 equals log 101 divided by log 3. It's always the log of the result divided by the log of the old base. To change that to a base we can work with. And now all we have to do is use a calculator and subtract 4 from both sides, and we have x equals 0.201. Right, so these really aren't that difficult. Not with logs helping us out. All right, let's look at another one. So if you can't rewrite the equation, so the base is the same, you're going to take a log of both sides, right? In the same base as the base of the exponent on each side. I'm going to go through them step by step, right? I didn't want to erase it because, well, it's written up there pretty nicely, including the steps. All right, so step 1. Here, everything's isolated. We're just going to take a log of both sides. There's no way I can write 15 as 2 to a power. It's an odd number to begin with. Certainly not power of 2 raised to some power. Property, the exponent can move in front. So I've got x times log 2 of 2 equals log 2 of 15. And by the way, make sure you're taking notes. I know some of these are in your notes. I think these are. All right, and so log 2 of 2, that's just 1. So that's just 1 times x, or x. And we're going to use our change of base formula. So we're going to rewrite log 2 of 15 as log 15 divided by log 2. Or you can use natural log of 15 divided by natural log of 2. Now, either one of these will give you the exact same answer. I just have a tendency to use base 10 for some reason. Oops. And I didn't write in the 15. All right, so you could just as easily use natural log of 15 divided by natural log of 2. When you plug that into the calculator, you get x equals 3.9068. So what that means is that 2 to the 3.9608 power equals 15. Well, that makes a lot of sense because that's really, really close to 4. And we know 2 to the 4th would be 16. All right, so let's look at the second one here. We have 10 to the 2x plus 3 power equals 8. Now we've got to isolate our exponential equation. So we'll subtract 3 from both sides. So we have 10 to the 2x equals 5. All right, so now we'll take a log on both sides. Now we don't have to use our change of base formula, by the way, because our base is 10. 10 is nice to work with. Right? We can work with that in the calculator. All right, so we have log 10 of 2x equals log 5. That kind of looked weird, like an exponent. It was so small. So log 5. There we go. All right, so now the power property, the 2x moves in front. Log 10 is just 1, because that's saying what would you have to raise 10 to get 10. You'd raise that to the first power. So now I have 2x equals log 5. I'm going to divide both sides by 2. I usually isolate my variable and then just plug the whole thing into the calculator. All right, so if you were asked on a test for the exact answer, that is technically the exact answer. So x equals log 5 divided by 2 is the exact answer. If we wanted the decimal approximation, that would be 0.3494. But you're actually not wrong to say log 5 divided by 2. Right? So there are 2 more for you. And let's do a couple more. I think. All right, so here I have 2 more. All right, so negative 5e to the negative x plus 9 equals 6. We're going to subtract 9 from both sides. So we have negative 5e to the negative x equals negative 3. We got to isolate that exponential completely. So we're going to divide both sides by negative 5. Okay, we can't have anything with the e, including a coefficient. So now we have e to the negative x equals 3/5. Now we can take the natural log of both sides. Right, and that will free our exponent using the power rule, right? Because we take natural log, right? Because e is the base for natural log, and e has the exponent. So now we have natural log of e to the negative x equals natural log of 3/5. Right? The exponent moves in front using the power property. So we have negative x natural log of e equals natural log of 3/5. But natural log of e, that's just 1. So there's no reason I have to have negative x times 1. I can just have negative x. But we're not looking for negative x. We're looking for x. So we're going to divide both sides by negative 1. So the exact answer would be negative natural log of 3/5. And if we plug that into the calculator, we would have x equals 0.5108. I always think it's best to isolate your exponent and then just put that into the calculator. All right, so now, unless I ask for the exact answer, then you don't have to put in the calculator. Just leave the isolated variable, and that would be a correct answer. So technically, if you said negative natural log of 3/5, that would be the exact answer. All right, so now let's look at the last one on this page. 7 to the 2x minus 9 minus 2 equals 43. We have to add 2 to both sides. Of course, we can't write 45 as 7 raised to a power. 49, yes. 45, no. So we're going to have to take a log, and the base is going to have to be 7. So log base 7 of 7 to the 2x minus 9 power equals log base 7 of 45. All right, that power rule, exponent moves in front. So we have 2x minus 9 times log base 7 of 7 equals log base 7 of 45. All right, so now we want to isolate our our variable. All right, so I don't need log base 7 of 7 because that's just 1. So we have 2x minus 9 equals, I'm going to use my change of base formula. All right, so because it's in base 7 and not base 10 or natural log. All right, so I have log 45 divided by log 7. And actually, I'm going to isolate this completely, even though I'm going to have to go grab a calculator. All right, and then I'll plug the whole thing in. So you can see what the exact answer would look like in case you're asked for the exact answer. So 2x minus 9 would equal, right, we just use the change of base formula. If we want to isolate x, I'd have to add 9 to both sides. So I'd have 2x equals log 45 divided by log 7, right, and then plus 9. So that plus 9 is separate, right? That's not part of the log. And then I'd have to divide both sides by 2. So my x here would be 1/2, right? Because it's a little easier for me to write 1/2 as opposed to divided by 2 here. It's going to look busy with I already have a fraction. Log 45 divided by, log 7. And that, I don't know what that looks like. Looks like log us. Log 45 divided by log 7 plus 9. And I took half of all of that, right, because I divided by 2 after I added 9 to both sides. Now, if you find that difficult to plug that into the calculator like that, and that's too tricky for you, feel free to isolate it the other way, all right, the way I had up there. All right, so actually I will add both of those. All right, so I'll just put a little star here. All right, if you don't like that, all right, but it's nice for you to see the exact answer. You could also do it like this. All right, so we had 2x minus 9 equals log 45 divided by 7. You could plug that into a calculator, and I'm going to get a calculator right now. Oh, I don't like that calculator. If I got to plug the whole thing in, I want a calculator I can see what I'm plugging in. All right, and that little baby TI is not one of them. All right, so log 45 divided by log 7 is going to give us 1.956. So even though this is a rounded value, it's okay to calculate with it because I'm just adding 9 and dividing by 2. I'm not plugging it into an operation. I'm just isolating x. So it's really not going to make any difference at all. And I'll use more decimals. 2, 4. There we go. All right, and then we would add 9 to both sides. So then I'd have 2x equals 10.95624. And then we would just divide that by 2. So that would be 5.478118. Right? Right, so that would be our answer there for x. All right, but either way, whether we do it piece by piece, we simply find that we evaluate the log and then isolate x, or we just do it all at once, isolate x and then plug that into the calculator, we'll get the same answer. So I'm just going to double check. I'm going to just plug that into the calculator, and I'm trying to hold the microphone at the same time, which is not easy. So I have log 45 divided by log 7, and then we're going to add 9 to that. Well, I hit evaluate. We'll add 9 to that, and then just divide that whole thing by 2. And quite honestly, I actually put that in step by step anyway when I plugged into the calculator, because I didn't want to accidentally put the 9 in with the 7. So I actually just did log 45 divided by log 7, hit enter, added 9, hit enter, and I divided by 2, which essentially is the same thing I did up here. Either way, I get the same answer. So this here would be considered the exact answer. And then this was our approximation, because that was a non-terminating decimal. Then we just kind of rounded. Right? So that's really all you have to do for solving using logs. Right? We're just using the properties of logarithms and using a log in the same base as whatever has the exponent to be able to free that exponent using the power rule. And then if your base isn't something friendly, then we just use our change of base formula. But here, this is an example of all the different kinds of problems that we could have in terms of solving exponential equations. All right, so we're going to do one more. I think that's the last one. And then you have a whiteboard practice. All right. So this one's kind of an interesting one. Let's take a look at this one. All right, so I'm going to subtract 25 from both sides. So I have 6 to the x equals negative 21. All right, and then we're going to take a log in the same base. So log base 6 of 6x equals log base 6 of negative 21. All right, so exponent can move in front. X times log 6 of 6 equals log 6 of negative 21. All right, so now that's just going to be x equals, and now I can use my change of base formula. Right? So this one here was we took a log on both sides. Right, and our base was equal to 6, right, because 6 has the exponent on it, and then we use the power rule. Right, and so now we use a change of base formula, and I write log so often. Let me use natural log so he doesn't feel left out. All right, so we have natural log of negative 21 divided by natural log of 6, and you plug that into your calculator. You can try this out, and you get the following message. Not change of base formula, but I wanted to write that down. That's what we were doing. So that was a change of base formula. You get this message. You get error or something along those lines. Why did you get error? Did you do something wrong? No. I gave you an equation that has no solution. That's what happened. Right? So a positive number cannot be raised to any power and result in a negative number. You raise something to a power, you're going to get another positive number. There will not be a solution to an exponential equation if one side of the equation is negative. You cannot take a log of a negative number. The calculator knows that there is nothing, and our bases will always be positive. 6 to what power equals negative 21? Not possible, right? It has to be a positive number. 6 to some power equal positive 21, yeah, that'll work out just fine. But to negative 21, that's not possible. So sometimes we do have no solution here. It is not a problem you needed to check because as soon as you tried to solve it, you found out that this does not work. This one had no solution. So on these exponential equations, you might have an equation that has no solution, but you'll never get a solution and have it not work out. If you solved it correctly, all your solutions will work out. If there's no solution, you find it when you try to get it using a calculator. All right, well, thanks for watching my podcast. See you later. Bye.